Hello, Chem 1B. This is Chapter 18, Lecture Video 9. So, in the last lecture video, we learned about non-standard Gibbs free energy, or delta G. Now, it follows the exact same rules as our standard delta G in terms of whether a process is spontaneous or not. In other words, the sign of delta G for a spontaneous process is negative, just like delta G naught. And for a non-spontaneous process, it's going to be positive, again, just like delta G naught. Now, one of the things that we need to talk about here is that when a reaction is at equilibrium, it's really spontaneous in neither direction, right? If you think about it, a reaction at equilibrium, that means the forward and reverse reactions are happening at exactly the same rate. There is no one side of our reaction that is favored at equilibrium. Now, there may be more of one thing, products versus reactants at equilibrium, but the rates of the reactions are occurring at the same rate. So if a reaction is at equilibrium, generally that's a non-standard condition. What would the sign of delta G be? Well, because if we're at equilibrium, we're neither spontaneous in either direction, our sign of delta G is actually 0. Delta G is equal to 0 when a system is at equilibrium. And this is something you should be aware of. Now, that is pretty powerful because it allows us to relate our delta G naught to the equilibrium constant. So our standard delta G can be related to the equilibrium constant using this relationship. So let's take a look at our delta G equation, right? We know delta G is equal to delta G naught plus RT ln of Q. But at equilibrium, we know that Q is equal to KEQ. That is something that we learned about in chapter 14, and we talked about it in chapter 16 as well, with KSP being equal to QSP. That's when we have a saturated solution, or in other words, when we're at equilibrium. Well, then we can do two things here. Let's say we are at equilibrium. Then I can kind of cross this guy out and in its place put KQ because of this relationship over here. Q is equal to K. And this guy has to equal 0. So if I do that all out, right? Well, would you look at that? I can relate delta G naught to our equilibrium constant now by just rearranging. So delta G naught is equal to negative RT ln of KEQ. And this equation here is one I will give you on tests and quizzes. But it allows us to relate our delta G to our equilibrium constant and vice versa. This is pretty awesome because delta G we can now calculate from our equilibrium constants. Now, equilibrium constants are heavily tabulated. So are our delta G values, both KQ and delta G naught. They're both heavily tabulated, which means if we don't know one, we can get the other. If we know the other, we can get, you get the idea, vice versa. We can get delta G if we know KQ. We now know if we know delta G naught, we can get KQ, vice versa. It's a big deal. It's important to recognize that only delta G naught is 0 at equilibrium. This guy is not 0 at equilibrium. Delta G naught is not 0 at equilibrium. Only delta G is, which is pretty important. So let's do a problem. We want to calculate what the equilibrium constant is for this reaction here. And let's say I need to go look up some values here. We're going to do it at 298. So the first thing I need to do is I need to calculate my delta G naught of this reaction if I want my equilibrium constant. Now I know that that's equal to products minus reactants of my delta G naughts of formation, all that fun stuff. So I need to look up all my delta G naughts of formation. But luckily these two are 0 because they're elements in their standard state. So really all I need to look up is my delta G naught for HBr. And here's my equation, right? Based on everything we've learned. Well, I have to go away and find my HBr, delta G naught of formation, which I did. It's negative 53.22 kilojoules per mole. That's 0 for H2 and 0 for Br2. And so 2 times this gives me my delta G naught of this reaction, which is this value. I can now take this and plug it into my equation we learned on the previous slide, that delta G naught of my reaction is equal to negative RT ln of KEQ. And these two I both know, and I can solve for that one because I know this value. If I rearrange this equation to solve for KEQ, I get this, right? E to the negative delta G naught over RT. Again, R is in joules, delta G naught is in kilojoules. You got to be careful about that. So that's why I'm multiplying it by 1,000 this time. And if I do all this out, you don't need to know R this far out. You can just kind of cross off those two if you didn't want to. I get my KEQ is 10 to the positive 18. I knew it was going to be a large value because this is negative, which means this is a spontaneous reaction, which means our equilibrium has to tell me it's a spontaneous reaction. In other words, my equilibrium constant had to be greater than 1, and I would definitely quantify 10 to the 18 as much greater than 1, pretty large. So spontaneous reaction. Again, just to remind you, we know 3 ways to predict spontaneity. We know delta G is less than 1. We know KEQ is less than 0 for that first one. My bad. KEQ is greater than 1. These are all spontaneous. And lastly, delta S universe is greater than 0. These are the 3 conditions that we so far know that tell us that a reaction is spontaneous. So if one of them is true, the other 2 also have to be true. Does that make sense? So if I get a negative delta G, that tells me my equilibrium constant is greater than 1 and my delta S universe is greater than 0. Hence, since we had this negative value here, we kind of should have expected a value greater than 1, which we got, which is good news. So let's look at this for the boiling of water at the normal boiling point. In other words, we have 1 atm of this guy at normal boiling point. Remember that when you have a normal boiling point, your vapor pressure equals 1 atm. You should have learned that in Chem 1A, probably in chapter 11. So if we want to know what our KEQ, delta G naught, and delta G are for this reaction, we can kind of figure that out. I know delta G naught, or delta G, sorry, non-standard is 0 because at the normal boiling point, this reaction is in equilibrium. So that's the first thing I know. I also know that KEQ is just equal to the pressure of H2O, which because we're at the normal boiling point is equal to 1 atm, which means KEQ in this case is equal to 1. because we're in standard state. Right? Normal boiling point tells us that the vapor pressure has to be equal to 1 atmosphere, which means that's our pressure of H2O gas present in the system. This again is kind of a hard pull from a definition that we learned in Chem 1A. Well, now at this point we can also figure out delta G naught, because delta G naught of our reaction is equal to negative RT ln of K, and K is 1. And so negative RT times the natural log of 1, well, this guy's 0. So we have negative RT times 0. In other words, in this case, delta G naught of our reaction is also 0. This is a very rare case. Most of the time you're not going to get this happening, and it's only because our KEQ is actually equal to 1 that it's 0. All right. At this point, one of the things you should recognize is we can calculate delta H and delta S to determine a boiling point or a freezing point even, because all we got to do is take our delta G naught of our reaction is equal to delta H naught of the reaction minus T delta S of the reaction. The temperature this is 0 at will be your boiling point, as we just learned, because this will be true for any system that's at its normal boiling point. Which means if I know this, if I know delta H and I know delta S, I can solve for the temperature this occurs at, and therefore solve for the boiling point. It's kind of neat. Now let's look at the differences between the different delta G's or Gibbs free energies that we've learned about in this chapter so far, right? We've learned about the non-standard delta G. We've learned about the standard delta G, and we've learned about delta G naught of formation, which is also under standard conditions, but it's more specific. So let's start with delta G. Delta G is the free energy change for a reaction at any condition. Could be standard, could be non-standard, doesn't really matter. Generally, we think of it as a non-standard condition, but if we're under standard conditions, delta G is just equal to delta G naught then. And this is the most general Gibbs free energy expression. Delta G naught is the Gibbs free energy change for a process or system in its standard state. So we're under standard conditions. However, because of our equation, delta G is equal to delta H minus T delta S, this does not necessarily mean we're at 298 Kelvin. When we assume delta H and delta S do not change with temperature, we can actually have a delta G naught value that's not at 298 Kelvin. Finally, we have our delta G naught of formation, and it's the free energy due to the formation of a substance, 1 mole of it, from the elements in their standard state. It is by far the most specific. It has to be at 298 when we're using these values in the system, or 25 degrees Celsius. And like I said, it's by far the more specific. We're talking about a very specific process, the formation of a substance from the elements in that substance in their standard states at 25 degrees Celsius under standard conditions. But these are our 3 different delta G's. As always, if you have any questions about anything, please feel free to email me or come to a discussion session.